First up this morning, we have Dr. Peter Schubert of Packard Engineering. Peter's association with the Space Studies Institute goes back 20 years or more. Peter, in addition to being a very nice gentleman and a very clever guy, is also a real spark plug. He's got so many things going on related to space development that I can't keep track of them, and I don't see how he does. So, Peter, please take it away.
Hey, everybody who woke up this early on a Sunday morning, you are true space enthusiasts. The topic of this session is engineering materials for non-terrestrial resources. The goal here is to find ways to do things bigger, better, faster. So we're going to hear 4 presentations on different elements of this overall architecture, and we'll start off with the first one, electrical energy storage using only lunar materials. So to get a permanently occupied lunar base, we have to persist through the lunar night, which could be as much as 354 hours. It has to be, of course, highly reliable or a redundant system that can survive any kind of a mishap. The baseload power options are nuclear power, which is a really clever engineering solution, but may not be politically viable. Beam power from orbiting solar-powered satellites is also a very good solution. It takes a lot of infrastructure. Our focus here is in looking at the first time we want to spend have our manned bases extend through the lunar night. So storage options include batteries and also fuel cells. With fuel cells, we have to have a lot of hydrogen. That's now a viable option with the discovery of abundant water at the lunar poles. Batteries are another option, and that's the topic of this discussion here. There's a lot of people working on battery technologies to try to extend those to get very high specific power ratios so that we can survive the lunar night with very low launch mass. Another approach is to be able to develop this from in-situ resources. So a very brief history of batteries. The frowny looking guy at the top here is Count Volta, who in 1800 first invented batteries. Batteries was a term coined by Benjamin Franklin when they're still doing cat hair rubbing against glass plates. He put a bunch of those together, got a really big voltage, really charged them up, lit his hair up. He says, this is a battery. So that name has stuck ever since. In the mid-1800s, the rechargeable batteries was first developed by Gaston Ponte, a French researcher. Edison in 1901 came up with the alkaline battery. This is still the biggest selling battery today. This is the Ever-Ready. This is the Duracell. So a battery is really a collection of individual chemical cells. Chemical cells have a potential, a voltage potential, that's dependent upon their materials. So these are typically in the range of 0.7 to 1.2 volts. So those are not very useful voltages, so you have to stack these together in a series to get to a useful voltage. That stacking of individual cells is the battery that Benjamin Franklin coined. So to do battery fabrication on the moon, the proposal here is to do an Edison cell. This concept originally came from Dave Dietzer, who's my co-author, and was not able to travel, so I'm presenting this paper for him. So this was developed by the Edison Battery Company from 1903 until 1972 continuously by the Edison Cell Battery Company. The half-cell reactions are shown on the right-hand side for the different anodes and cathodes. There's iron on one side, nickel on the other, and potassium hydroxide is electrolyte that's in between. These are very simple, common materials, and they're available on the moon. The electrolyte, we need to have water for this. Now that we've got water at the poles, this is now a viable solution for making batteries with in-situ resources for our robotic precursor mission before the people land with their habitat and need to plug in. The casing for this can be cast basalt, or it could also be a polymer-lined container that we make out of bricks. So what are the storage requirements for a 2-person base, our first base on the moon? What we see on the right are 2 different concepts for a lunar base that will be exposed to cosmic rays. This is not the long-term base, but in order to get to the point where we can start bootstrapping things up from the robots first, and the humans come to put together a larger infrastructure, and then get to the point where we eventually can bury this underneath, as we heard yesterday. This is bridging that gap. So we're assuming that we need 1.2 kilowatts for a 2-person base. 1.2 kilowatts is what your house draws for a typical 4-person house in the United States. We also compared this to the the LEN module and found out how much power that had for 2 people with a 75-hour trip with the moon. That was 1.02 kilowatts on an average basis. So we figured this is a reasonable number for a 2-person base. We want to give 100 square meters. We're assuming, actually this has changed. The equatorial location was scratch that because there's no water there. So that should be polar location. For horticulture, to support life, we need about 20 square meters per person. So if we use red and blue LED lights, it's been shown that you can get the power to 100 watts per square meter for horticulture. So we use that in our power calculations. Here we're assuming that inside we've got a short-sleeve environment, and outside we've got a very cold environment, as cold as it gets in the moon, pretty close to absolute zero. So with variable, this could be better, but we're going to make a worst-case assumption. So there's 2 ways to get iron and nickel out of lunar soil. There's more than that, of course, but the 2 that we studied. The first was to magnetically harvest fines. These fines are left over from iron and nickel meteorites that hit the surface. They're often associated with silicates. They're clustered on those. So we crack those off with a grinder. Then the MON process, which was invented over 100 years ago, is to use carbon monoxide to be able to dissolve these metals. So we make this very toxic material called carbonyl, which has a very cool property of being a gas that we can heat up and then cause it to precipitate out. Because iron and nickel have different temperatures at which they form carbonyls, and once those precipitate out, we can use a fractional distillation to get these 2 different metals out. The second method is more of a brute force approach. You can see that in the image that's in the back. This is a way where we can separate these things from a plasma beam by the charge-mass ratio. This is similar to a mass spectrometer on steroids, according to Dave. I've got 3 patents on this process, and we're doing this work at Packer Engineering, as Lee mentioned. So this same process can also extract silicon and aluminum. The output of this thing, the stuff that doesn't ionize, is dolomite. That's calcium oxide and magnesium oxide. Those CaO and MgO molecules are really robust. They don't melt very well, so they make a really nice slag. So we can use that brick to form the vessels for this container, bring some lightweight polymers like Teflon, line that, and be able to make our battery cells inside there. To get potassium, there's not a whole lot of potassium in the moon, but there are places where there are more bodies. One way to get this out is through vacuum roasting. If you roast it between 900 and 1200 degrees C, you can get up to 30% of that potassium out. To verify this, we also looked at studies of the lunar atmosphere and found that there is some potassium in the lunar atmosphere, rare as it is, which shows that even sunlight pinching on the surface of the moon can cause some of that potassium to come right out. So the alternate is the extraction method shown on the previous page, where here we're trying to separate things by charge-mass ratio. Now potassium, some potassium is radioactive because it's a decay product of other naturally occurring radioactive materials. It overlaps almost exclusively with calcium. And calcium, there's a lot more of that in the moon. Fortunately, one of the isotopes of potassium, the most abundant one, K40, is sufficiently separated from calcium that we can extract that. But if this extraction isn't that accurate, if we get some contamination between those, we've got another thing in our favor. Once you throw these metals into water, the potassium dissolves much more readily than the calcium does. The calcium is just going to sit there like a lump of rock. So we get the potassium hydroxide we need, and we don't care about the contamination with calcium. So that's a benefit in making this thing simple and robust. To get the water, of course, we got water abundant at the poles. We've assumed here at 85% insulation, and this is supported by the talk that Professor Smoots gave yesterday. If we have 2-meter masts, a study that was published at Space 2010 shows we can get up to 90% sunlight availability. The vessels can be made from cast basalt. Cast basalt is used traditionally on the Earth. What we're showing here are some cast basalt crucibles and other different kinds of structures that have been made from melting this material and squished it into a form. You can make this into a vessel. The neat thing about this is that cast basalt can withstand up to 50% caustic solutions. We only need a 30% caustic solution for the Edison cell. So this stuff should be able to be used directly as is, without a liner. The only trouble is that there's not much basalt at the poles. If you go to the lunar north pole, there's some basalt that's pretty close by. So there's some issues there on whether we want to import basalt or just, people we've got there. We've got the other choice of the dolomite slag that comes out of an isotope separation process. Our guiding principles in this have been to try to find methods that have other applications for a lunar base and have at least 2 ways of doing everything so that we've got a more robust architecture for doing not only batteries, but all the other things you want to do when you have a lunar base. So we've assumed that each battery is a cubic meter of water. It's somewhat arbitrary. These are some of the specs. Edison cells range from 0.03 to 0.05 kilowatts per kilogram. We use the middle number for that. The leakage rate is shown. Deep cycling is how far you can cycle your batteries down before they don't work anymore. In your lithium-ion batteries or in your cell phone or your laptop, those don't go down very far before you have to charge them back up again. That's why you always have to keep charging in that battery. But Edison cells are deep cycling batteries, like marine batteries. They can go down to a very low level, get a lot of that charge out before you have to charge it back up again. So we figured that 65%, even though that specific power is available, you can only use 65% of it before your electrolytes force your reaction back the other way. We've assumed 24-volt operation. This is suitable for pumps and motors and communications and most things. It's kind of like a car, but a little bit higher, so you've got enough power to be able to do stuff. We assume electrode mass, kind of on the high side, is 0.5 metric tons per battery. We're assuming that we're just going to cast our iron and nickel electrodes, so they're going to be big, ugly, stupid things. There's nothing fancy or high-tech about this, and that's the benefit of it. We can have simple, dumb robots be able to process this before the humans come and need to charge up. There's also heat loss. Whenever we got the lunar night, this thing is going to vacuum as an R value of 50, but that means we are going to lose some of our heat out to the environment. So we figure that we're going to have self-heat. So the self-heat is going to reduce the available power in our system. This schematic shows how to distribute this. We've got two PV arrays, again, for redundancy, assuming these are masked. We have a weighted parallel circuit breaker. Then we have a transformer for the helostat to be able to follow the sun. Except one of the poles, we're just going to be twisting around in a circle. We assume that the lunar base is going to be some distance away where we need to have some kind of transmission system. So we boost this voltage up, transmit it down, and then return it. There's one battery system that's put at the place where we're collecting the solar power. So we've got all of our energy collection and storage in one spot. And then once we bring this into the base, now we've got a second battery that's redundant to that, that's at the base itself. That way, if you have any kind of mishap, you've got an ability to get your power from the other place. So this is kind of an eye chart, but these are all the detailed calculations of the storage system and then the needs for the base, including the heat loss from the base itself, assuming we don't have any insulation. We didn't even bury the thing. So we made worst case scenarios for this two-person base. We come up with a total of 6 batteries. So these are cubic meter batteries like this size. We need 6 of those. With redundancy, we need to have 12. The logistics, we're assuming here that the water harvesting is already being done by some other smart people who are going to the base with us. So we've got this water available. We're kind of ignoring that part of it. The iron extraction, we've got 2 different methods for doing that. We can get up to 16 batteries per year by the isotope separation, and about 3 times that for the magnetic extraction. So the magnetic extraction does require carbon monoxide, so the carbon would have to be brought with us along this thing. It'd be part of the factory. The factory launch masses are shown down here. They're relatively small. The Altair lander, which was part of the Constellation program, could carry 6 metric tons to the surface of the moon. So these things are very feasible in terms of what we're talking about sending to the moon and be able to process this. So in conclusion, we've got electrical energy storage. We can do this with only lunar-based materials, plus an Earth-launched ISRU factory with robots and with water available. And in 1 year, 1 Earth year, we can serve up to 2 to 3 continuously occupied, fully located, two-person bases. Thank you for your attention.
Wow.